If you are a real estate investor, you're constantly making predictions. Whether you're trying to estimate what rents will be in the future, the level of vacancies, or what will happen to inflation going forward, your investments will depend on the level of accuracy in your predictions. Two aspects of data that are super important, but often omitted by investors when making projections, is the variability or dispersion of the data and the margin of error they're willing to tolerate in their predictions. These are two sides of the same coin. Let's have a look at two data sets with the exact same mean but different levels of dispersion. Let's assume we are projecting the mean level of rents in a certain market, which our data tells us is 18 euros. The blue line represents a data set with a standard deviation of 1 euro, and the orange line is based on a data set with a mean of 18 euros and a standard deviation of 2 euros. The standard deviation is a metric used by statisticians to measure the average dispersion of the data with respect to the mean. Despite the ugliness of the formula, it is fairly intuitive. We mentioned that standard deviation is the average dispersion of the data about the mean. Dispersion is measured as the difference between each data point and the mean. Now, because some of these values will be negative and others will be positive, and what we are really interested in is the average dispersion, we have to take the square of the difference before we add them up. Or otherwise, the positive numbers would cancel out the negative numbers. Once we have the sum, we divide by the sample size to give us the mean difference squared. We then take the square root of the mean difference squared so that the standard deviation is expressed in the same units as the variable itself. So, if our data is the average rent in euros per square meter, for example, the standard deviation will be expressed in euros per square meter as well. Going back to our data, recall that the blue line is based on a data set with a 1 euro standard deviation and the orange line on a data set with a 2 euro standard deviation. This is reflected in the shape of their distributions, with the orange data set much wider than the blue. Now let's say you're looking to make a projection for the average rent over time based on this data. How would your projection differ depending on which data set you pick? That will depend on the level of confidence you're looking to associate your prediction. The level of confidence is the opposite of the margin of error. The more confident you want to be in your prediction, the smaller the margin of error you will tolerate. If we assume the future will behave the same way as the past, your most probable bet about the future rent price is 18 euros, which is the mean value. If you want to be more precise and incorporate a confidence interval, you need to have a look at how the data is distributed. If the future behaves like the past, the confidence interval is the range of values extracted from the dataset that will contain all the possible future values of the variable you are projecting, with the margin of error that you specify. Let's say the confidence interval we're looking for is 95%, or a margin of error of 5%. For the blue line chart, the margin of error spans the values from 16 euros through 22 euros per square meter, or 2 standard deviations. For the orange chart, the 95% confidence interval spans the values from 14 euros through 22 euros, a much wider range of values than we saw with the blue line. Now, you can tell by the smoothness of these lines that these graphs have been extracted from a perfect distribution, meaning that it is the result of a math formula that expresses what the perfect normal distribution with means of 18 euros and standard deviations of 1 euro and 2 euros would look like. Let's have a look at a more realistic example. For this example, I have created 2 samples of data by using Excel's random number generator. Here's the formula that I have used. Both datasets have a sample size of 50 occurrences and a mean of 18 euros. The standard deviation for the first sample size is 1 euro and 2 euros for the second. Each data point is randomly generated and has no correlation with the prior data point. Once we have this data, I have created frequency tables to look at how the data is distributed. What the histogram does is it creates these bins and counts the number of occurrences in the data that fit within each bin. So for bin 19 euros, for example, the number of occurrences is 8 and 7 for each dataset, respectively. If we plot these frequency values into a histogram, we can see how the data is distributed, which is the chart you have on the right. As in the previous example, you can see how much tighter the data on the blue chart is in comparison to the orange, which is much wider. For each distribution, I have calculated the relative frequency of each bin. So the 19 euro bin, for example, comprises 16% of the total data in the blue data and 14% of the orange data. With a relative frequency, we can look at how we'll have to set the ranges so that we arrive at confidence intervals of 95% in each scenario. You can see those shaded here as well in a lighter color. The ranges span from 16.5 euros to 20 euros for the blue data and 15.5 euros to 21.5 euros for the orange data. These ranges differ from the ideal values we obtained in the previous slide, where they were obtained from a formula, but they are close enough. The reason they are not the same is because our sample size is small. The greater our sample size, the more the values of the sample will approximate the distribution predicted by the normal, or the one derived from the formula. One interesting thing we can observe for this dataset is the occurrence of outliers, which are these two instances we observe in the orange data. The greater the dispersion of the data, of which the standard deviation is a measure, the greater the possibility for the occurrence of these outliers. So, in order to provide a complete picture when you're running projection, you have to provide the mean value and the confidence interval that will give you the margin of error you feel comfortable with. I have created a small example to see how this variability in the data would impact a hypothetical calculation of exit values based on these levels of rent. For each dataset, we obtain the mean rent and the low and high values based on our 95% confidence intervals. Assuming a GLA of 1,000 meters squared, OPEX of 20%, and a 6% cap rate, these are the mean NOI values we obtain, which are very similar in both cases. 14,589 for the blue data and 14,701 for the orange data. The low and high values corresponding to the 95% confidence intervals of each dataset are provided here, with the blue data range for NOI above and below the mean value a total of 10%. For the orange dataset, the low and high values represent a variation of 15% and 17% from the mean, respectively. So how do we use this data if we are looking to estimate the fair market value of this property at acquisition? The conclusion here is that if the blue dataset is what I'm working with, then I'd feel very comfortable with a purchase price of 220,000 euros, knowing that 95% of the times, the value of the property will be above this price. If orange is the data I have to work with, then I would have to buy this property at 206,000 for my margin of error to be 5%.